Okay, hi everybody. We're going to take a look at some sample problems that deal with friction. And the first one here, we're looking at a box of delicious Junior Mints, which is the best candy. It's my favorite candy. I love Junior Mints. And it's a 3 kilogram box, so it's pretty big. A 3 kilogram box of Junior Mints. Between the box and the floor, we got a coefficient of static friction of 0.4 and a coefficient of kinetic friction of 0.25. And they ask us, what is the box's acceleration if you exert a force of 10 newtons and if you exert a force of 15 newtons? What a great question. I wish I could meet the guy who wrote it. Okay, so in part A, 10 newtons force. Well, of course, anything, we want to start with a free body diagram. So I'm going to draw my little dot. Hey, looks like a little Junior Mint. And I'm going to think, what are all the forces acting on this Junior Mints? Well, the boring directions, you might think, is the up and down. We got gravity, of course. I'll write it as mg. Why write F sub g? It's just mg. And then the normal force of the ground pushing up. Now we're applying, let's call it a force to the right. We'll call it F ap. That's my force to the right. And if this problem is correct, we've got friction in play. So friction is pulling to the left to fight the direction of motion. So if I think, okay, there's my free body diagram, my next part of my recipe is F net equals ma, and I gotta, of course, think of these as vectors, so I gotta think about the x and y direction. Let's call up and to the right positive for this particular problem. So I'm gonna call the side to side direction, we'll call that the x direction. If I do it for the x direction, I would say, okay, my applied force minus my friction force equals ma. Okay? But the question is, here's my friction force, which flavor am I dealing with? What kind of friction? Is this box moving or not? I don't know. We better test it. Let's take a little different color, and we're going to do a test. Let's see if this thing is going to move at all. So my static friction max, we know from the previous video and what we talked about in class, is going to be equal to mu sub s times the normal force, right? Well, guess what? We can figure out what the maximum force that friction exerts is. We happen to know that the coefficient of static friction is 0.4. We know that the normal force in this case is going to just be equal to weight. Hopefully I don't have to show you that. We've done enough of those so you can see. But we can just calculate the weight, which is 3 kilograms times 9.8. And if you put all this in your calculator, you'll find that you'll get about 11.8 newtons. So if you'll notice here, what is happening? The static friction maximum force is greater than my applied force. So what's that mean? Well, it means that it's going to be pulling back with 10 newtons of force, right? It's not pulling back with this. This is the maximum value. It doesn't mean it's really pulling back with that. But if I apply 10 newtons of force this way, it can pull back with up to this value. So basically, I'm trying to tell you that it doesn't move. It doesn't move. So it doesn't move. So, everything cancels out. So guess what my acceleration is? It's 0. It's 0. My acceleration is 0. That's what they're asking me. Boy, that was a trick question. But not really, because look at this. Now they ask us in part B, what about 15 newtons? What about a 15 newton force being applied? Well, looking at this, I know, because, and I bet you'll agree with me, that 15 newtons is greater than 11.8 newtons. So it's greater than the static max. So we know it moves. So it moves! Exclamation mark. So what kind of force are we dealing with? Kinetic friction force now. So we got to remember that in our equations that we're dealing with kinetic friction. Switching colors, and then we're going to say, okay, F net equals ma. I'm going to do that in the x direction. Now I'm thinking kinetic. So that means my applied force minus my friction force, my kinetic friction force, equals ma. I happen to know that my applied force is 15 newtons. They told me that, and I know that my actually, let me not throw in any numbers yet. My applied force is just my applied force, but I know that friction, this term of friction, is really mu sub k times the normal force. That equals ma. And even more than that, I know that this term can be unpacked to be mu sub k times mg, right? Because that's what my normal force is equal to. So I can write it full-blown just like that, and I'm running out of room here, but I'm going to write it anyway. So I got 15 newtons minus this coefficient of kinetic friction. They told me what that was, 0.25. times m, 3 kilograms of delicious mince, equals m, well that's 3 again, times a. And so what do I end up getting? I get an acceleration. When I crunch all this out, divide by 3, acceleration is going to be 2.55 meters per second squared. There it is, 2.55 meters. So it's moving. That's 2.55 meters per second squared at 15 when I'm pulling with 15 newtons. Okay, well, let me ask another question. They didn't ask it, but I'll ask it here. By they, I mean me. I wrote this. I won't lie to you. Let's just remind ourselves that, okay, okay, this is the breaking point, right? That's the point where this thing broke free and started moving. What if my applied force happened to be just slightly above, I'm going to go ahead and say equal to 11.8 newtons. That value that it's going to make it break free. Let's say 11.800000001. Okay, so just enough to make it move. Well, what would happen would be that the friction would immediately switch from static to kinetic. So I would have an equation that would look like this, just like I've seen before. And if I think to myself, okay, my applied force now is 11.8 newtons, and I can calculate my kinetic friction just like I did down here of 0.25 times 3 times 9.8 equals 3 times a. And if I solve for acceleration here, I'll get an acceleration of 1.47 meters per second squared. So even if it just breaks free of friction, it's going to accelerate. It's not going to move at constant velocity. It's going to accelerate. So that's why that sensation of things popping free. So anyway, that's a good one for horizontal stuff. What about something? Oh my gosh. Oh my gosh. Are you seeing what I'm seeing? I'm seeing an inclined plane. That means this is going to be awesome. I got my penguins again. No more living in a frictionless world for you guys. You're now on an inclined plane with friction. And they've asked us some things. They said, oh, I forgot to write that in. That's theta. If our static friction coefficient is 0.4, what's the angle required for this box to slide down the slope? Ooh. Good question, right? Because if the angle's too shallow, the box will just sit there. But as it goes up, something is going to try to pull this box down the slope. What would it be? Let me draw a free body diagram. I'm going to start off by saying, well, I got to remember on my inclined plane stuff, and you can see a previous video on that. The weight's pulling down, normal force from the surface pushing out like that. My weight is really broken into two forces, one going down the plane, one going perpendicular to the plane, and this is the same angle as that one. But now, no longer am I in a friction-free world. I got friction. So what's going on? You'll notice that there's a little piece of gravity pulling down and friction pulling up. They're the ones at war, okay? So I'm going to say down the slope and perpendicular to the slope is positive. Let's see what we can get when we work some numbers here. Let's do red. Red's cool. Okay, U sub s equals 0.4. I got that. If I do this in the y direction, let's see what happens. F net equals ma equals 0, right? Oh, you know what's going to happen. Normal force minus mg cosine of theta equals 0. So that means my normal force is going to be mg cosine of theta. Huh. So it's not mg anymore. It's mg cosine theta. That's useful because we need to know the normal force when we do things in the, wait for it, in the x direction. That's right. So if I do it in the x direction, let's see what's going to happen. F net equals ma in the x direction. I'm going to have, well, what is in the x direction? By the way, I just jumped right in there and said that was mg cosine theta. Let me just remind you, you are dealing with a right triangle here, so that means that this part of this component is mg cosine of theta because it's adjacent. This part is mg sine theta. I didn't write that out, but it's worth noting. You can look at a previous video to see that. Okay, what am I doing? I'm using blue. Let me do this here. That would mean if I did this, I would get mg sine of theta. So mg sine theta, what is that? This, the force pulling down the slope, is in a tug of war with friction, and that equals ma. Okay. And if I'm looking for the situation where it's just required for the box to slide, I'm going to go ahead and say that this is my what? My static max. which means that it's just enough to make it break free, so we're going to call acceleration 0. So we're looking for the situation where mg sine of theta equals my static max force, friction force. Okay, well, what is that? Let's find out. So my static friction maximum, we know that is mu times the normal force. Oh, wait a minute. This is my normal force, so I got to do mu mg. By the way, it's mu sub s. Mu mg cosine of theta. What does that equal? Mg sine theta. Wait a minute. You notice I didn't give you the mass of these penguins. Wasn't that clever of me? Because guess what? Mg cancels out. It doesn't matter. So I get g sine of theta equals mu sub s. Oh, sorry. No g. That's a messy looking S anyway. Let's start all over. Oh my gosh, something disappeared up here. I think it was a G. MGs are gone, so we got sine of theta equals mu sub S cosine of theta. If I solve for mu sub S, what do I get? I get sine of theta over cosine of theta. That's tan theta, people. Yeah, trig. And so theta in this case is going to be inverse tan of my coefficient of static friction, and in this situation, because that is 0.4, that, you can check your calculators, gives you 21.8 degrees. Boom. There we go. What else can we do? Well, let's see. It asks me down here, at that angle, this angle, with a coefficient of kinetic friction of 0.2, what is the acceleration then? Hot shot. Well, we can do that. It moves, so now we're dealing with kinetic, right? Kinetic. Hi, my laptop's bouncing all over the place. Earthquake. So this is kinetic friction, so we're going to use that now. Let's look in the x direction again, and we're going to say mg sine of theta, this is kind of what we had up here, minus the force of kinetic friction equals ma. Now, I'm not looking for sort of this break-free criteria, so I can't say acceleration equals 0. I got to keep this here. In fact, we're looking for acceleration. But I can think about and unpack what this friction force is, right? It's mu sub k times the normal force, but guess what? Yada! I know what the normal force is, so it's really mu sub k mg cosine of theta. I just got to use mu sub k now instead of the other. So I got mg sine of theta minus mu sub k mg cosine of theta equals ma. Masses go away. G doesn't. G's not over here, but the masses go away, so that doesn't matter. So my acceleration equals g sine of theta minus mu sub k g cosine of theta. And what's interesting here is that this is exactly the this part is what we got when there isn't any friction, because if mu sub k equals 0, this whole term just disappears, goes away, and that's what leaves us with that little piece. Now, if you were to plug these numbers in, 9.8, 21.8, mu sub k of 0.2, what you're going to find is you get 1.82 meters per second squared. So at that angle, when it just breaks free, the minute it breaks free, it doesn't just slowly slide down, it's got some acceleration. It's going to really be changing there. So that was, I would call that a challenging problem. So that's good stuff. So hopefully this gives you enough information to go back and look through, and we'll look through some more examples in class.